Very good. Thank you. Thank you very much.
شو عملتم؟
Oh, السلام عليكم دكتور.
عليكم السلام ورحمة الله.
Yes. Now the participants, they are joining now. Okay, Engineer Abdullah, you are welcome.
Welcome, Dr. Mudassir. Good morning.
Good morning. Thank you. Good morning, everyone. We are starting now soon. Welcome to this important session and to this important webinar. Please, for the participants, if you have any question, you can write your question in the Q&A. Also, for our panelists, please make sure that you have a stable internet connection. We are going to start soon our session. We will have an opening remark. And then after that, Professor Joel will moderate this session. After that, we'll have a Q&A session. And then we'll have a panel discussion. And finally, we will wrap up this session. Thank you. Thank you very much. Okay, good morning again. On behalf of the Executive Director of the Nile Basin Initiative Secretariat, Engineer Silvista Matemo, I would like to thank all the panelists and welcome all the participants on this webinar about hydrological modeling and river flow forecasting. The Nile Basin Initiative, in collaboration with the government of Uganda, is organizing a series of webinars in the 7th Nile Basin Development Forum. The Science Policy Practice Dialogue is organized to bring together MBI with its stakeholders from Nile Basin countries and around the world. The theme of this forum is deepening Nile cooperation, accelerating the achievement of SDGs in changing climate. The goal of the 7th Nile Basin Development Forum is to enhance transformation processes in projects that will contribute to the Nile Basin Initiative shared vision, which is to achieve sustainable socioeconomic development through the equitable utilization of and benefit from the common Nile Basin water resources. The themes under this 7th Nile Basin Development Forum are adaptation to climate change, water supply and sanitation, water resources management, basin investment plan, groundwater, water quality, and transboundary water governance. The Nile Basin is one of the most critical transboundary water basins in Africa, with the River Nile playing a crucial role and source for the most economic and social activities for the countries in the Eastern and Northeastern Africa. The Nile Basin Initiative developed several systems like Nile Basin River Flow Forecasting System, the Drought Monitoring and Forecasting Tool. So I would like to welcome you to this important session about hydrological modeling and river flow forecasting session. We hope that these different forecasting systems will provide valuable insight and help in making informed decisions regarding hydrological forecasting systems. Let us have fruitful presentations and discussions, and let us work together to incorporate these findings in our decision-making river basin agenda. Thank you, and welcome again to this webinar. And allow me to remind you again about the title of this session. It is Hydrological Modeling and River Flow Forecasting. I would like now to give just a brief about our moderator, Professor Joel. Professor Joel is an associate professor and director of Institute of Water Resources Assessment at University of Dar es Salaam. He is trained at University of Dar es Salaam and also Yokohama National University, Japan. And he has specialized in hydrology and water resources management. He has conducted various studies in the area of water resources management and hydrological modeling. He is currently leading the team in the development of integrated water resources management and development plan for Lake Victoria Basin. He has participated in the development of integrated water resources management and development plan of the internal drainage of Ruvubu Basin in Tanzania as an expert in water resources modeling, and also DSS component, which are World Bank funded project under the Ministry of Water Resources. Thank you. Thank you. And back to you now, Professor Joel, for moderating and leading this session.
Okay, thank you very much for the introduction and for the opening of the session. Thank you very much. And now I think we can go then straight to our presentations, to our sessions. And yeah, the session has already been introduced as it's hydrological modeling and river forecasting. And we are expecting to have 5 presenters today. And we were supposed to start with Anika. I'm not sure if she's in the house. If not, then we can start with Dr. Sentayehu Gebre.
Yes.
Yeah, good. Then let me just give a brief bio for Dr. Sentayehu. Dr. Engineer Sentayehu Legese Gebre is a consultant professor in hydrology and water resources engineering at Jimma University in Ethiopia. He has over 10 years experience as a water resources engineering consultant and lecturer at renowned institutions, nationally and internationally. He holds a PhD in engineering science from KU Leuven University, Belgium, MSc in hydrology and quantitative water resource management from Wageningen University, the Netherlands, and MSc in irrigation engineering from Abamich University, Ethiopia. So that is Dr. Sentayehu. And he's going to do the presentation on optimizing transboundary water allocation, a decision support tool to meet water, food, energy ecosystem demands. So I'd like to welcome, maybe let me introduce, okay, and I'll be introducing them before they present, so maybe you can go straight to the presentation. So maybe Dr. Sentayehu, you can go straight with your presentation, and then I'll introduce the rest of the speakers as their session comes.
All right, okay. Okay. Good morning, everyone. And thank you for inviting me to present one of our work on this platform. And I think you can see a full view of the presentation. So the title is that optimizing transboundary water allocation. It is just like developing or implementing a decision support tool to meet the water, food, energy ecosystem demands across the transboundary water or river system. So what is the theory behind that? That we have a global problem, that high population increase and urbanization and also industrialization, which contribute to reducing of carbon dioxide and also high energy demand. And also we have also pollution, environmental pollution, most of the time from agricultural waste product like fertilizer, excessive use of fertilizer, and wide use of land management. That contributes to a pressure on the available limited water resources, especially transboundary water river system. So this increases the high population and urbanization, and also the environmental pollution will create its own pressure on water, food, energy, and also on ecosystem demand. So we need to think about how we can able to manage and optimize the water resources so that we can allocate the demands for water, food, and energy, and also as well as for ecosystem, so that we can able have a sustainable river system or water resource flow across transboundary river system. So this creates, as I said, that there is water for food production, like for irrigation, and also water is needed for energy production, for hydropower development, and also there is water for environment or ecosystem. So there is a high competition for accessing of these resources. So we need to come to the point how we can able to address systematically simultaneously all those demands so that we can optimize the limited water resources so that we can able to sustain the resources and avoid unwanted conflicts across the transboundary nations. So the multifunctional demand that we have come up, every stakeholders have its own interest, and we need to come up and search a tool or a decision support that can able to analyze these conflict demands. So then the main gap is that due to lack of decision support tools that address water allocation problem, is initiated to develop such kind of tool. So the tool is that this is a schematic overview of, we have a river flow from upstream to downstream across different nations. So we have different demands. Water is extracted for irrigation, and water is extracted for water supply, and also water is extracted for industrial energy demand. And also there is an environmental concern. There should be a minimum water flow across the river so that the ecosystem demand can be met. And also there are downstream, or at the downstream side, there are stakeholders who needs their share. So we have to, there is a complex demand, so that we need to compromise all those demands and able to allocate the water accordingly to each demand, so that we can able to sustain the flow of water, and as well as we can meet the growing demand of water, food, energy, and ecosystem. So we come to as a stakeholder, and we come together and discuss. Then after that, we put inputs, then analyze and develop the model. Then we have the share resources along stakeholders so that they can able to use the resources and as well as sustain the river flow. So this is a schematic presentation of the model. We have a flow of water flowing, and on each river segment, then we have also reservoir which feed water to farm one, and also we have water extractor to meet the hydropower demand of industry directly from the river, and also there is also water extractor directly from the river to farm too. And also we have another reservoir along the river, which water is extracted from the reservoir to the city as water supply. And also we have a pond, which is to maintain the ecosystem. So we have a pond, also water is diverted and stored into the pond. And also we need to have a certain amount of water should be allocated to the downstream. So this is a schematic presentation of the model. We have different, for instance, input flows like rainfall, and also each river segment is divided, and this river segment is calculated using a Musinga water flow, so that's able to realize the practical situation of how water flows in a natural river system. So that is the detail. I don't want to go to that, but this is the way how we can able to allocate the water to meet the water for food, and water for water supply, and water for ecosystem, and water for energy demand. And also we allocate certain amount of water to downstream, so to avoid unnecessary conflict. So this is the mathematical models developed that the objective that to minimize the associated costs with transporting water through reservoir links, while also penalizing unmet water demands for food or energy or for ecosystem. So this is a holistic way of addressing of each aspects. There is economic part and also social aspects and the technical aspect and also environmental aspect are integrated. So we try to address the different aspects. So it's kind of a holistic system that can compromise all the environment, technical, social, and economic aspect of along the river basin. So the model is simulated, and this is the reservoir water volume storage for the two reservoir. One is for the irrigation water farm, and the other one for water supply. And the model easily simulates the water storage in the reservoir. Also, this is the water allocation for different water demand flows, water demand for the industry, for water supply, and also for the pond, for ecosystem demand, and also there is unmet water demand for industry and also for water supply and also for ecosystem. And also the other thing that this model also maintains a minimum amount of river flow that also able to meet the river ecology beside the pond ecosystem. So that, and also at the end of the downstream, there is a certain amount of water is allocated to downstream demands. So that means the model able to meet the different demands and allocate water along the river to the transboundary conditions. And also this is the irrigation water allocation for two farms. The one farm is directly connected with the reservoir, and the other one is directly connected from the river system. Water is extracted from the river. As you can see that this is simulated for a 1 year period on a weekly basis. The time span is weekly basis, so that it's able to simulate and able to meet the demands of irrigation water demand or water for farm. So that is in short the simple presentation of the model. And then if anyone is interested, I will share the detail of the model, what it does. So the general conclusion is that we this is a Gabriel model allocate the available water to the different water users and producers, and optimal solution consider the dynamic water availability. And the model is flexible and versatile, can able to accommodate large scale data, and also can be applied at watershed level, at river basin level, or at regional level. And also the decisions can be prioritized, helping intervention investment, particularly in transparent water resource management, to promote fair water sharing and facilitate multilateral cooperation and collaboration rather than unilateral investment and water utility to meet ecosystem demands. So this model able to address the different growing demands of water, food, energy, and ecosystem, and allocate the water along the river basin. So this is a general concept of how this mathematical decision support tool is able to allocate the water in a river system, especially in transboundary water system. This model have been applied in Omotor Canal River Basin, and there are different reservoir and also water demands along the basin. So the model has been tested and it produced a reasonable result, and also that can be also validated with observed data. So in the future, we try to apply this in a Nile basin where there is different complex interaction in water resource demands. So we will try to apply in the Nile River basin and come out with a research output, so that can be able to give information for decision makers to allocate the water to different nations according to their demands. So that's all about. If you have any question, I will address later in the panel sessions.
Okay, thank you very much, Dr. Sintayo, for that interesting presentation. And maybe if there is a quick comment from the members in the group, or if you have any quick question.
Okay, is there any question on that?
Maybe Professor Joel,
Yes, please.
maybe after the presentations, we have like a slot for the Q&A.
Okay.
And then after that, we have the panel discussion. So maybe we can allow now all the presenters to present now. And then later, we can capture from the Q&A button the questions of the participants. Thank
All
you,
right.
Professor Joel. Thank you.
Thank you very much. So with that, then, thank you very much, Dr. Sentayo. Then we can go to the next presentation.
All right. Okay. Thank you.
Thank you very much. And the next presentation is going to be by Dr. Osman El Tom Hamad. Dr. Osman holds a BSc from University of Khartoum in 1971, an MSc in 1975, and PhD in 1995 from Newcastle University, UK. He worked for the Ministry of Irrigation and Water Resources from 1971 until he became the Minister for Water Resources, Irrigation and Electricity in 2019. He represented Sudan as the NILTAC, NSAP, and panel of expert member from 1997 to 2004. He worked with Nile Basin Initiative as the water policy lead specialist from August 2004 to December 2008, and also as the individual consultant for the project planning and management from June 2009 to December 2010 in Addis Ababa, Ethiopia. He's an associate professor for project management master course in 5 Sudanese universities. So that is Dr. Osman, and he's going to do the presentation on mathematical model for predicting the annual Nile River flow at strategic sites. Dr. Osman, please welcome for your presentation.
Thank you very much. I hope you are seeing me.
Just a quick comment here.
Yes.
Can you just also, Professor Joel, can you put your video on, and also Dr. Osman, so you allow our participant to know our speakers? Thank you.
Thank you very much.
Okay. Thank you very much for allowing me this opportunity to present to you on this lovely day, I think. For us, I am presenting from Saudi Arabia, from Ad-Dammam. The co-author of this presentation is Sami Osman Atom. I think he is on travel now. I would like to, let me put this down, okay? This is the introduction. I think I'll skip this very quickly. This is introducing the River Nile. I think you know about this, and all of you. But I would like to give you an idea about the model that we have developed, the two of us. This is the Nile situation in an average year, and it's on a spreadsheet. The information is fed at the borders. A dam here, which is just downstream Gerd, Malakal in South Sudan, and Hamdait and Al-Asirra. This is just before the upper Adbara complex and after Tekazi in Ethiopia. This is where we are putting the information. The model works after July, August, September, and October during the flood. So it is forecasting the recession period. So what the input data are put here. When I say JASO, that is July, August, September, and October. So for this, the upper Adbara or Adbara River, and this is for a dam, Blue Nile, and this is for the White Nile, and it goes on schematically to reach Aswan or the high Aswan Dam. The annual flow at the borders is about 100 billion cubic meters or kilometers cubed, 100. But when it reaches Aswan, even if there is no obstruction or anything, it reaches 84 billion cubic meters. And this is what the figure that is known for so many people, because the 1959 agreement was based on this 84. This 84, if I say it quickly, it is 48 for the Blue Nile, 24 for the White Nile, and 12 for Adbury River. So it is in the ratio of 1, 2, and 4, 7. So this difference is the transmission losses within Sudan. Here, what you are seeing here is the typical average year with all the information about it. A lot of information are you can pick them from here. I'm not going to go further on this. I'll go for the rest of my presentation on this. Okay. Now the model does two things. It forecasts the Nile recession flow from Jadu that I told you about it, the flow at the borders. So if you know July, August, September, and October at the borders, then you can estimate or forecast the annual flow during the recession period. This is done here, for example, this is for Malakal. This is the Jazhu, and here is the annual. The relationship is a straight line relationship, and you can see that R squared is 0.93, and the formula is there. So whenever you know Jazhu, you can easily tell what is the annual flow for that one. This is for Adbury River. The relationship is even more smooth because Adbury River before Tekazi and Upper Adbury complex used to dry out after January, but now with Tekazi and the complex, there is always flow downstream Khashmal Girba, and this is a blessing for the people from Khashmal Girba up to Adbury. They used to suffer a lot. So this is the relationship, and you can see that R squared is very high. It is 7% only during the rest of the year. When you have Jasu flow, the rest of it is only 7%. This is for the Blue Nile, and this is the dominant feature of the Nile, whether in Sudan or anywhere. And this is the relationship, and you can see that this is a very good relationship. But we went further to forecast during the recession period every 10 days. And we have developed this equation. Then Q naught is the flow during the first 10 days of November. And then QT is for the next ones. For example, here, T is 0 for November 1. When we say November 1, that means the first 10 days. 1 for November 2, 2 for November 3, and so on, up to March. The forecast is done up to March. Why? Because April, May, and June, this is the start of the rise of the flood. So we take the long-term average for that one. And after all, it's not a big amount of water during that period. So this forecast is tells you much more. As you can see here, again, I don't want to take your time on that, but it is not only JASU, it is a function of JAS, which are the 3 months, July, August, and September, and October by itself. And here, this is a very interesting P annual. P annual, that means we discovered that there is some sort of a succession that if there is a dry year, then it affects the flow, recession flow next year. And if it is a wet year, then it makes it a bit higher. So introducing this previous annual flow gave much better results for that. This is now I would like to talk about the transmission losses along the Nile from Ger to High Aswan Dam. This work has not been done before. The transmission losses, they were always assumed. Some people say 10%, some people say 15%, some people say 12%. Here we ventured to try to calculate the transmission losses. How do we do that? We have the famous water balance equation. Q out is equal to Q in minus the abstractions, whatever they are, and the evaporation losses, the transmission losses, and the change of storage if we are working in a dam. Here we have chosen a period when there is no dam, so there is no change of storage. So there is no evaporation losses from the dams because there are no dams. And at that time, abstraction in Sudan was very small, very, very small. So we took the time from 1915 up to 1923. That is just before Khazan Sinnar or Sinnar Dam started to be in operation. So during that period, it was natural flow from the borders up to High Aswan Dam. At that time, High Aswan Dam was not there. There was Aswan Dam, the small one. So, and then we extended the data even further to get more realistic data. And here we added from 1928, that is after Sinnar started to be operating and Jazeera started to take water, up to 1932, that is before Jabal Awliya Dam. So this gave us, because we have added the evaporation losses from Sinnar and the abstraction by Jazeera scheme during those years. So putting that in the equation, we could calculate transmission losses. You can see here in this equation, very easy. The only unknown is the transmission losses. And then we checked our data from 1966 up to 2006 with abstraction of Sudan for each year to see whether we are on the right track. And then again, we said that let us check the transmission losses, not between Adem and Aswan, but between Adem and Dongula. And that one gave good results as well. And so we went on. This is very interesting again. This is the transmission losses from Adem to Aswan. And you can see how straight line it is. This is the data from 1915 up to 1932. And they went very well. Even R squared is only 1. Here we have compared the model results versus the measured flows in a number of key stations. Aswan, Tumaniyat, north of Khartoum, Khartoum, the White Nile, that is from Jabal Awliya, and Khartoum, the Blue Nile, that is coming from Sinnar. So you can see the points. If we put the line 45 degrees, it is more or less passing through. Here we are doing the same information, but this time we have put the trend line. trend line, you could see that R squared is more, very close to 1, and Y is equal to X. That means the model results match with the measured flows. This is concluding now what I have been saying. What is important about this model is the review of the transmission losses and the calibration that I talked about and everything. Here, and comparing the results with the flow measured at the executive bodies of the Permanent Joint Technical Committee, PJTC, between Sudan and Egypt. They are doing the measurements at the different locations. The model is characterized by its transparency and flexibility that allows for adaptation to any new changes or updates of the system. So this is very important. Being on a spreadsheet, it is very transparent. You can see everything, and it is flexible. So if I go back to the model here, the model, if you change the value here, everything changes. If you change it here, everything. So you can use it for each and every year. This model you can easily see. This is the flexibility. It even goes further to include Manandaya and Biko Abu and Karadobi, and Tana Balos is already there, and Cherichera is already there from Tana, and here we have the Sud area and Victoria. So if we would like to have the whole system of the Nile, if there are any dams here or obstruction or anything, you can easily add that in. You can see here, Jabal Awliya, you have all the information, Sinnar, Roseris, Dindir and Rahad, and so on. So very flexible. You can see that Sudan obstruction, if I can quote that one, is 14.3, much less than the quota given to Sudan through the 1959 agreement. You can see this is an average year. So the water released from the high Aswan Dam is 61.5. The Egypt share is 55.5. So there are 6 billion meter cube out of the share of Sudan going through the high Aswan Dam to Egypt. Maybe this will not continue like that because Sudan couldn't use all its share because the storage capacities that we have are limited. But with GER, maybe the situation will change. Thank you very much.
Thank you very much for the great presentation. And yeah, then thank you very much. We'll come back to Q&A later. And I think we can go for the next presentation. And I'm assuming Engineer Abdallah is in the house. Engineer Abdallah, are you around?
Yes, sir.
Okay,
Right.
thank you very much. So the next
Thank you.
presentation is going to be from Engineer Abdallah Mohammed.
Yes, let me share my screen.
Okay, maybe let me give you a bio a bit briefly before you present.
Yes.
And so Engineer Abdallah is a holder of MSc in Surface Hydrology from the Indian Institute of Technology, India, in 2014. BSc Civil Engineering, Sudan University in Sudan, 2008. He is currently the UN FAO National Project Coordinator for monitoring water productivity through open access of remotely sensed data, WR2 Phase 2 project. He works at the water resource as the water resource engineer, Ministry of Irrigation and Water Resources, Sudan. He has over 14 years of work experience in hydrological measurements and modeling, bathymetric survey, water resource management, remote sensing and GIS application in irrigation and agriculture. And his presentation is going to be on monitoring and reporting water productivity and irrigation performance using remote sensing, WRPO, to accelerate achievement of SDG 6.4 and 2.1 goals. Case study of Gezira Scheme, Sudan. Welcome, Engineer Abdallah, for your presentation.
Thank you, Professor Goy, for the introduction. Yes, I will be presenting a case study we conducted in Gezira Scheme to report and monitor water productivity and irrigation performance. So before going into detail, I would like to dive into water productivity as a concept and how it can serve as indicator for agricultural and water use. So why water productivity? This topic is one of the most important topics.
Abdallah, if you can put in presentation mode, please.
It is not in presentation mode?
It's not full screen, I think. It's still in the slideshow. I mean, put in a slideshow maybe.
Is it okay now?
Not yet. Maybe if we can go to slideshow.
Yes, I put it in the slideshow.
Or you can just press F5 and.
Is
Maybe
it
you
okay?
have two screens. Do you have two screens? You might be with an extended screen.
Is it okay? Or
No, it is not.
It's not.
I will share my screen again, okay?
All right. Maybe you stop sharing and then you share again. Yeah, I think this is okay.
Is it in the slideshow now?
Yes, it is.
Professor Goy.
It's okay. Go. It's now it's fine. Now it's fine. Hello? Jen Abdallah can hear us?
رجعت تاني يا عبد الله كده شوف السلايد شو.
Is it in a slideshow now?
Not yet. The other one was in slideshow, but we could not hear you.
It was in a slideshow.
Yeah, it was in slideshow before, and but we could not hear you.
Okay, I will share my screen again.
That's better.
This is okay.
Okay.
Good.
So as I said, this water productivity topic, it is become a most important topic to tackle global growing water scarcity. As you know, there is a high rate of population growth and thus high water demands, and also a climate change become a reality. So we need to use the water more efficiently, especially in agricultural sector. Why in agricultural sector? Because agriculture is responsible for 70% of fresh water consumption in the world. So what's water productivity? Water productivity is generally defined as crop yield per cubic meter of water consumption, simply crop by drop. And therefore, to improve water productivity, we need to increase the production and minimize the water consumption. As I mentioned earlier, we use FAO WAPO portal. WAPO is the FAO portal to monitor water productivity through open access of remotely sensed derived data. And WAPO gives users freely access to a wide variety of satellite data, such as biomass, actual evapotranspiration, net primary production, precipitation, and so on, which can be used to calculate water productivity and also irrigation performance. Now, the WAPO database covers the whole Africa and Near East, as you see in the web portal. And from the 4th of October, the database will cover the whole globe. The data is freely available on wapo.apps.fao.org. We conduct this study in Gezira scheme, and the Gezira is the largest irrigated scheme in Sudan, and it is covered around 900,000 hectares. And the scheme is consumed 6 billion cubic meter per year of Nile water in Sudan, which is 50% consumption of Nile water in Sudan. The scheme produces the half of country agricultural output and consisting of around 129,000 farmers. So the objective of this study is to assess the current level of production of productivity and yield gap and of the wheat crops, and also irrigation performance in Jazeera scheme, and also to recommend measures that can improve water productivity and irrigation performance, and finally to propose compendium of implementable solution and policy relevant issues to accelerate the achievement of SDG 6.4 and 2.1 goals. Regarding the methodology we follow to analyze the water productivity and irrigation performance, first we collect local information for the study area, such as the scheme boundary, start of season, end of season, and so on. And then we download the data from WABOR portal using Python. We calculate the water productivity and also the bright spot and performance indicators, and also we use QGIS to determine or to locate the high and low productivity area. And then we use Kobo Toolbox to create a questionnaire for the farmer interview to know the reasons behind the high and low productivity. And from the analysis of the questionnaire, we come up with conclusion and recommendation to increase water productivity. This diagram shows the flow of data processing calculation. For the time consideration, I will not go into detail on this. It's available also on WAPOR web portal. Yes, we generate these maps from the WAPOR database. The first map on the left shows the water consumption in Jazeera scheme, and the second map shows the production. And when we divide the production by the water consumption, we get the water productivity, the third map. As you can see in the red box, in Managil zone, we have high water productivity fields with a fairly high production and low water consumption. The yield range from 4 to 6 tons per hectare, and the optimum is 6 to 9 tons per hectare, while water productivity is about 0.4 kilogram per cubic meter, which is less than 50% of the optimum for wheat crops. The optimum is 0.8 to 1.6 kilogram per cubic meter. And in the north zone of the scheme, highlighted in yellow box, this zone is struggling from low water productivity with low field production, but also low water consumption. And this area needs urgent intervention. And in the south zone of the scheme, highlighted in light blue box, it is mixed zone of high and low productivity. For south and north Jazeera zone, the majority harvest less than 2 tons per hectare, and water productivity is below 0.3 kilogram per meter cube. And as I mentioned, we also calculate the irrigation performance. We calculate the adequacy. Adequacy can be defined as the sufficiency of irrigation delivery compared to the requirement. It is equal to seasonal actual evapotranspiration divided by the seasonal potential evapotranspiration. The performance of the irrigation network considered poor if the adequacy is less than 0.68, and acceptable if it is range from 0.6 to 8 to 0.8, and good performance if it is greater than 0.8. And as you can see in the graph, 86% of irrigation divisions in the scheme shows poor performance with adequacy less than 0.68. And from the map, you can see we have high adequacy in south part of the scheme and low adequacy in north and west part of the scheme. So the intervention can be prioritize based on the adequacy value. And we also calculate the equity. The equity is the evenness of the water consumption between fields within the irrigation scheme with homogeneous crop. So equity is equal to the coefficient of variation of actual evapotranspiration. The distribution of water in irrigation system considered good if equity is less than 10%, and fair distribution if it is range from 10 to 25%, and poor distribution if it is greater than 25%. And as you can see in the graph, all irrigation divisions in the scheme shows fair distribution. And this map shows the equity on the irrigation division. And you can see we have relatively good uniformity in South Jazeera and West Managil zone, and poor uniformity in north part of the scheme. Yes, from the analysis of the questionnaire of high and low productive farmers, we come up with best agricultural practice for wheat crops, and these practices have been transferred to the farmers through farmer school, field days, and so on, and farmer organization. Yes, the recommendation, we recommend the implementation of the compendium of the solutions and policy relevant issues, which is one of the output of this study to accelerate the achievement of SDG 6.4 and 2.1. So the solutions consist of 4 pillars. The first one about irrigation system operation and maintenance. So we recommend efficient use of machinery and also the proper execution of desiltation campaign. And finally, the new approach of private sector involvement. And regarding the second pillars, which is about on-farm water management, and here we recommend adequate implementation of the existing irrigation schedule and crop rotation, and also introduce remote sensing supported monitoring system. And finally, all farmers should adhere to the agreed upon size of irrigable area in a given season. The third one is about agronomic and farming practice, and here we recommend adequate cooperation between Jazeera irrigation staff and farmer, and also the Jazeera inspectors, and follow the 50% rule of cultivated land, and also raise the awareness of the farmers and build the capacity to adopt the new technologies and sustainable practice that align with proper practices. And the fourth pillar is about institutional arrangement and farmer organization. And here we recommend update of irrigation and drainage law, and also establishing of justice offices for the irrigation issues, and also to organize a workshop, raise awareness about the cooperation among the stakeholders, and finally create determination of roles and responsibility of each partner through integrated and cooperated approach, and existence of legal bodies such as water association, water user association. And generally we recommend also, since WABUR data is available for the whole Africa, this study can be replicated in each of irrigation scheme in the Nile Basin country. And also WABUR portal can be used as an innovative tool to monitor and report on water productivity. Okay, thank you. Thank you.
Okay, thank you very much, Engineer Abdallah, for that presentation on water productivity monitoring. Yeah, then questions will follow later, and then I think we go to the next presenter, and I'm just checking if Mr. Karim Soliman is in the room.
Yes, I am here.
Okay, thank you very much. So you'll be the next presenter, and before you present, I would like to give you a short bio. So Karim is specialized in the field of water resource engineering with almost 6 years of experience in particularly in hydrology, hydrogeology, as a site construction engineer, a design engineer, a research assistant, and project engineer. He holds 2 master's degrees from Technical University of Darmstadt in the field of hydrogeology in 2021, and Cairo University in the field of water resources engineering in 2021. He got his bachelor degree in the field of water and environmental engineering from Cairo University in 2014. He got enrolled in projects related to design of storm and sewer drainage system, hydrological and groundwater modeling, design of flood protection systems, construction of flood protection structures, data analysis, climate change analysis, and bias correction of the climate change and satellite meteorological data. So presentation from Mr. Soliman is going to be on modeling the wetlands of the Nile Basin. Welcome, Mr. Soliman, for your presentation.
Thank you very much, Professor Yoel, for this introduction. Let me share my screen.
Mm-hmm.
Can you see my screen or not?
Yes, we can see.
Can see, but can you duplicate?
Yes. Okay, okay.
Yep, I think that is better.
Can I share? Can I try to share once more?
Yes, yes, please.
Is it right now or?
I think you still need to duplicate. It has a small window. The previous one was the best. I mean, the one which you showed before, you had shown before this one.
Just go on your screen on top, the second button and the drop down. Then you click it to duplicate the screen.
Where?
On the top, at the top.
Okay.
Taskbar. Put your cursor, the second option. Yeah, hit that, the lower one, duplicate the lower one, that one.
Okay, okay, thank you very much. Okay. Okay, firstly, I would like to thank the Nile Basin, NileSec, for giving me the opportunity to present our work in the Nile Basin related to the wetland modeling. Maybe I can introduce myself very briefly. I'm Karim Soliman. I work currently at Cedro Consult, Darmstadt, Germany, in the field of water resource engineering as a project engineer. And we are working with several projects related to the Nile Basin, related to the strategic water resources assessment, SWRA, and also related to the climate change infrastructure services. So this work is considered as one of the assignments that we are working with the Nile Basin, which is modeling and improving the wetlands of the Nile Basin, especially for the SWRA model. So why we model the wetlands? So modeling of the wetlands is very important to understand the water balance of the Nile and how could we understand that? We need to understand the water balance of the Nile in order to see the impact of the water infrastructure development in the Nile Basin, and also see if the wetlands are degraded, what will happen related to the drainage or related to the greenhouse gas emissions. So in case of the wetland degradation, what will happen in the Nile Basin system? And also we need to understand the hydrological behavior in the wetlands in order to manage the floods and droughts in the system. And also we need to assess the ecosystem benefits and services that could be gained from the wetlands. So here in SWRA, in phase 2, we found that we need to conduct a new approach to model the wetlands in order to get accurate results in terms of volume and surface area of the wetlands. And we developed that using TALSAM NG model. This is a hydrological river basin model, which is developed by our company, CEDRO. And we try to model the major wetlands in the Nile Basin, including Mashar Marshes, Sood and Bahr al-Ghazal in South Sudan, Lake Yuga and Similiki Delta in Uganda, and the lower and upper Kagera, which is shared between 4 countries, Uganda, Tanzania, Rwanda, and Burundi. So let me explain briefly what is nested modeling. So it's basically, it is a model inside a model. So in the, suppose that we have this basin, as you can see in this figure. We have a big basin with different sub-basins, and we are going to model that in a coarser model. And now we need to focus on a smaller scale, on a sub-basin. And this sub-basin, we need to represent it or simulate it at finer resolution in terms of time step, in terms of grid size. And within this sub-basin, okay, the inner model will have smaller time steps so that we get more accurate calculations of the hydrological system or of different hydrological components. And at the end, the inner model contributes to the outer model, and they are connected together so that they could be like a one model. So this nested model is considered as a grid-based model consisting of grids, or we could say it's a spatially distributed model. And it's consisting of grid cells with connected together by a flow network of the sub-basin. And each grid is represented as atmosphere vegetation soil interface model, where different hydrological variables are simulated, including the precipitation, evapotranspiration, percolation to the groundwater system, base flows, interflow, and also the surface runoff. And in this modeling, we tried to introduce the estimation or evaluation of the carbon dioxide emissions of the different wetlands. So I will go very fast through the model setup in our model. So firstly, we try to collect data related to the study area. And I took here an Similiki Delta an example. So we collected the digital elevation model and also the using and also different satellite images to delineate the wetland catchment area and also to delineate the mainstream flow of the wetland. And then we try to generate the flow network of the system. And also we collected soil texture data, and we found that the soil texture, the study area were almost loamy clay, and land cover, and we found that the land cover consists of agricultural activities, grass and sharp lands, and also wetland grasses. And there's some cells which were represented as open water, representing the permanent wetland in the system. Before we go to the model calibration, also we gather data related to the precipitation and evapotranspiration using rainfall satellite estimate datasets and also reanalysis datasets. And during the calibration, we try to calibrate the discharge at the outlet of the wetland. And we found that the mean monthly of the simulated time series is matching with the observed ones. We didn't conduct calibration for the daily time series due to lack of data availability for a long time period. That's why we tried just to calibrate the mean monthly discharge. And as you see here, you find that the mean monthly discharge of the simulated model is matching the observed one in terms of the seasonal cycle or the monthly variation. We try to validate our model, and we have conducted that by downloading remote sensing data sets, which is processed for specifying the surface water extent of the wetlands. And we tried to download two kinds of data sets to improve our validation of the model, including the Copernicus land cover and the Joint Research Commission of European Union. And we found that also it's almost matching, but it's not 100% perfectly matching. What was matching was a seasonal cycle or the seasonal pattern, but the peak of the surface water extent of the model was different somehow from the satellite datasets. And here are the results showing the wetland status in terms of the inundation depths and the soil moisture. And you could see the change in the wetland status every month. And you could find, and we have distributed the status according to the inundation depths and soil moisture. So the saturation occurs at water level greater than 0. Wet conditions occurs at water level greater than -1. Storage at water level greater than -2, and dry at water level greater than -3. And also the soil moisture, we have conducted also classification based on the soil moisture characteristics, including the field capacity and the wilting point. And based on this classification, we could identify at which months the wetland is considered as saturated or we could identify also whether the wetland is considered as a permanent wetland or not. So now we go to the next step, that we need to quantify the ecosystem services of this wetland, and we try to correlate a relationship between the water hydrological characteristics, including the soil moisture and open water conditions. And based on that, we could quantify or assess the ecosystem services. And we found some literature which had conducted an assessment of the ecosystem services related to fish, papyrus, livestock, the carbon stock loss and purification. And this studies has been conducted at different wetlands in the Nile Basin. Like, for example, the fish was conducted in Sud, papyrus was conducted in Uganda, and livestock also in Uganda. Carbon stock loss was conducted on the whole Nile Basin. And also the water purification was conducted on a case study in Uganda. So how could we relate this work to the key actions for the Nile Basin in order to deepen the Nile cooperation? So we could relate it to the ecosystem. So wetland should be assessed to understand the water availability, the flood retention, and other ecosystems of the Nile Basin, and also climate change. Wetland, if it's degraded, it will be a greenhouse gas emitter and contributing to the global warming. That means that we need to manage the wetlands in agreeing with the stakeholders and the local stakeholders, especially in order to avoid or mitigate the degradation of the wetlands. So finally, the conclusion. So I think the model is considered as an innovative step to consider the wetlands with more comprehensive description of the wetlands in more depths related to the water depths and soil moisture, and how could we correlate it to the ecosystem service assessment. We could say that the results of the wetlands shows reliable results in terms of the discharge of the wetlands to the Nile Basin or to the main streams of the Nile Basin, and in terms of the surface area extent. In order to increase the credibility of the model, we think that we need to gather more information data related to the socioeconomics for each wetland in order to estimate more precisely and more reliably the wetland ecosystem services or benefits. So thank you very much for listening, and I'm ready for any questions that could encounter related to the project.
Thank you very much, Mr. Soliman, for this interesting presentation on the modeling of the wetlands in the Nile Basin. And just checking if Anika has joined.
She's not here.
Anika is not here, and maybe Nile Seko can guide me. Is there anybody else who is in the house who is supposed to present? I don't see anybody else.
No one else.
No one else. Okay, thank you very much. Yeah, so if that is the case, members, and we had 4 presentations, and I think now we can move to another session of Q&A. Yeah, so maybe you can go ahead for maybe Nelsek, we can help you if there. You can let me check if you have questions on this.
Yes, on the Q&A, there are like some questions. If you click on the button
All right.
for Q&A.
All right. Mm-hmm.
Yes.
Okay, so let me go through the question. The first one is from Akiliu, I think, Alemar. How do you develop the recession equation for the blue case, for blue Nile case? It is not clear, and I think this goes to presentation.
Yes, this is mine.
Yes, on the modeling of predicting forecasting the flow.
Yes, thank you for the question. Actually, I was expecting this question, the recession equation. This is part of my PhD work. It took me about 1 year to develop that equation. The most important thing about it is that the recession is a function of the combination of jazz, which is July, August, and September, and October by itself influences the equation, and then the annual flow in the previous year. So those are the three factors that influence the equation, and started with Jazu at the beginning, as you saw, and then started to develop it more, and I found that you have to have October by itself. It is going to, it brings the results better. It is difficult to explain it in few words, but if you can download my PhD, it's a chapter by itself. So I can only tell you about it. So many PhD students after me, of course, that was in 1995. So many, so it is nearly 20 years now, or even more, followed that equation and developed their work on it. So I'm sorry not to give you a straight answer to that one. You need to look it up. Thank you.
Okay, thank you, Dr. Osman. I think I'll go to the next question. So we have requests from Mr. Mohamed Salih. Can you ask your question, please? From University of Sorbonne, Paris, France.
Yes, thank you. Can you hear me?
Yes, please, we can hear you.
Yeah, thank you very much for these interesting presentations. I go directly to the question. In the model presented by Engineer Tom, given that in the pipeline there are more than 20 new dams to be erected along the Nile Basin as a whole. For example, in South Sudan, 3 new dams should be built in the future. Will this model predict the presence of these new infrastructures which are coming in the future? And in such a case, do you think that the river basin will be naturally running river, or it will be human controlled and coordinated, which necessitate the cooperation among the stakeholders? In addition to that, also you mentioned that there is an excess of 6 billion cubic meter of water running to Egypt every year. What is the reason that it is running in excess? And always we see in the media there are complaints about the scarcity of water and also diversion of the water in Toshki and that things. Thank you very much.
Thank you very much. Let me start with the last one. Yeah, according to the 1959 agreement, Sudan share is 18.5 and Egypt share is 55.5. This is measured at Aswan. But the consumption of water in Sudan is in central Sudan. The corresponding, if you add the transmission losses between central Sudan to Aswan, which is about 13 or 14%, then you will find that Sudan share in the center of Sudan is 21. It's not 18.5. I don't want to talk a lot about the 1959 agreement. I see Sami is there around. At the time when this 1959 agreement was signed, Egypt population was 25 million, and Sudan was 12. Now Egypt is more than 110, and you can easily see that. This is why I am against the idea of quota. I agree with benefit sharing, and I have a presentation on the 2nd of October on that one, together with Engineer Sami as well, again. So this is the case. Why Sudan is leaving 6 billion cubic meters out of its quota going to Egypt? The reason is that the storage capacities in Sudan are not enough to capture that one, for the simple reason that during the flood season, Sudan opens all its gates in the dams, especially Roseris and Marawi and all of the dams, except Jabal Awliya, because of the silt. If we start storing water during the flood season, then we are storing silt water. Now with the GERD is going to capture 85% of the bed load. The silt is either suspended or bed, and so it's going to capture most of the bed load, and that would give the chance for the dams in Sudan to recover a little bit. But the most important thing is that is going to regulate the amount of water coming from Gerd to Aswan to Roseris Dam, and even to the Nile, is going to be regulated to a certain extent, because they need to generate hydropower generation, and so they have to release water during the dry season, and this we have seen it happening last year and this year as well, and we expect that is going to continue. In that case, then the storage capacities in Sudan will be reasonable, and we can store water at an earlier time, and we can make use of the flow coming from GERD throughout the year. Actually, in my paper that I'm going to present on the 2nd, I'm going to go more in depth to that one, because GERD can help the High Aswan Dam as well, but that will come later on. If you can remind me of because that one captured my attention, but the other one, yes, the other dams, the future dams which are going to be on the Nile, yes, this is the flexibility of the model. The model you can easily put in any dam or any abstraction point. You can put it there, put the characteristics for it, and you link it with it, because this is the beauty of using the Excel or the spreadsheet type. You can easily connect it through equations, and then you can add anything. Yes, the Nile is already controlled, and the system is getting more complicated as time goes on. And I think it will continue like that. But this is not surprising because Tennessee Valley and all those Danube and the Rhine and other things, other rivers, they are all controlled. There is no transboundary river that is flowing easily. Very few, in most of the world. But this is why we need modeling, and we need to understand the system, and we need, as some people have presented, and we have to see how we can cooperate on working on that. Otherwise, there will be a chaos. I think cooperation and coordination is is becoming very essential as the system gets more complicated. Thank you very much.
Okay, thank you very much, Dr. Osman. And yeah, I'll go to the next question. Is on the WAPO data and the water productivity. So the question is, WAPO data, is it applicable only for Africa? And how do we calibrate the data from WAPO? So I think this goes to Engineer Abdallah, I think.
Yes, the WAPO data right now, it is only available for Africa and Near East. But from the next week, there will be a launch of the version 3 data on raw water dialogue. It is on 4th October. And this version 3 data covers the whole world. So from the next week, the data will be covering the whole globe. And regarding the calibration of the data is already calibrated by IHE Delft Institute in Netherlands. And also the quality assessment report is available on the WAPO website. You can go through it. Thank you very much.
Okay, thank you, Mr. Abdallah, Engineer Abdallah.
Yeah.
Okay, do you have any other quick question from the group here, or a question if you have not written your question? Otherwise, maybe I can also ask some few questions. Okay, if no, maybe let me go to Dr. Sintayeu, and is on the optimization of transboundary water allocation. As you know, when you talk of water allocation model, it has mainly two components. One is hydrological modeling. You're talking of the water flow in the system, and then the water allocation component. So I didn't hear much on the hydrological modeling part, and how did you calibrate your model, and which kind of model did you use, and kind of assumptions put into the system? Maybe you can elaborate more on that one. And then related to that one again is the water allocation model. Your presentation from Dr. Osman, he talked much about transmission losses as well. So in your case, I want to hear, how did you take care of evaporation losses, transmission losses, for example, and also the groundwater and surface water interaction? Whether the assumption, I don't know whether you considered groundwater or is only the surface water allocation system. So how did you take care of that interaction between surface water and groundwater as well? If you can respond to that one first, and then I can ask maybe another question again.
Okay, thank you very much for the question. Yes, transmission losses, you could, in some people, they think that transmission losses includes percolation, evaporation, other things for the river system as general. But evaporation losses are calculated at the dams from the lakes. And that is easy because you have the evaporation depths, and then you have the area of the lake, and then you can easily calculate the evaporation loss at any time, whether on daily basis or monthly basis or even yearly basis. And this is done as part of the work. But here, in order to calculate the transmission losses, we had to find the period when all the other elements are zero. So the evaporation, there were no dams during that time from 1915 up to 1923. There were no dams. And there were very little abstraction, and there was no evaporation, no delta S, no. change of content and others. So the only variable was the transmission losses. When you get the transmission losses, then when you know that one, then you can go back to the equations and then you can calculate each one. The abstraction from the river, that is done by what we call for brother factors. You can easily, if you know the crop and the crop water requirements, you can easily calculate that one. So you will be left with the evaporation losses in the lakes, and then you can check with that one. The beauty of this model is that it checks the measurements that the executive bodies in Sudan and Egypt calculate at the key stations. So if, because it gives you what is the amount per year that is passing through a certain key station. And if it is different from the measurements, people will go back to the measurements and maybe check the rating curves, the method that they are measuring things and other things. And so you can get more reliable results instead of depending on what they have measured and considering that as accurate. So this is one of the beauty of this model, that you can check all the key stations along the river from the Ethiopian plateau up to the Mediterranean, if you extend the model there, and even you will have the SUD area will have a problem with you, but otherwise it is useful to, if you can model it, and some people have done that, modeling the SUD area, and I think somebody today, Mr. Karim, has presented some work on the wetlands. So this is what I can say. If you have any more questions, I'm ready for that. Thank you.
Dr. Osman, thank you. And maybe I go to Dr. Sentayo.
All right. Okay. Thank you, Professor John. Thank you for your question. I just want to reflect on that. In this model, we only just focus on the amount of water flow on the river channel. And for the hydrological routing, we use the modified masking method to calculate how the water moves from one segment to another. So as a catchment level, if you want to apply the model at a specific area, then you can use any hydrological model to calculate the stream flow. But in this case, we just only consider the amount of water flow on the river. So we use observer stream flow data. Then after that, we take some observer stream flow data for the long river. Then you can calculate the amount of the hydrological routing using the modified masking method, calculate how the water moves from one segment to another. And also when you discretize the segment along the river, it depends on considering of different things on the topography and also on the river channel and cross-sectional area and so on. All those factors are considered when you discretize the segment, so that you calculate each segment and how water flows from one point to another. And also based on that, so that we just only consider the amount of flow on the river, then we, the model, try to take the amount of water which is abstracted from the river channel and it allocates to the different demand nodes. Then we use actually the Lingo script to develop the model and to work it and to analyze. That's what it is. So we didn't use actually any hydrological model. If you want to hydrological model, actually we use for a practical river basin. This is a generic model. I just presented how the model performs. It's not specific to a certain location, but how it can be applied onto a transboundary river basin. And we applied in certain area for like on Umo river basin and how water is allocated. And we try to know the amount of water flow to each river segment. Then we can you can calculate that. But in this specific presentation, that is only focused on the amount of water flow on the river, and the hydrological routing was done by using masking modified method.
Okay, thank you very much, Dr. Sentayo. Maybe just one additional question is on because in the system we have the competing water users, and especially when you talk of hydropower systems and irrigation systems within the network. I didn't hear much about how do you set some priorities? How do you handle these conflicting water users in the system?
Yeah, actually, we didn't set prioritize. If you prioritize, it's not you're not going to optimize, you know. So
Okay.
yeah, we don't prioritize, you know. So we put all the demands. So we consider the different constraints, and we said that the whole system as one. We didn't categorize, you know, either the irrigation or the water supply as priority. So that's not this model is able to analyze the whole system at one, so that able to generate and optimize the allocation water for different demands. But if there is unmet demands, there is penalty for that. And also the demand depends upon, for instance, irrigation. If you have large scale irrigation, the amount of water demand is known. If you are not satisfied with that demand, actually there is an extension of on this model where the land allocation is integrated into the water allocation model, especially on a large scale irrigation scheme. And when there is no sufficient amount of water, so that you can select different types of crops which needs less amount of water. If there is excess amount of water along the river, then you can the model selects. I mean that there is no any problem with that one on water deficiency, so that any crops can be allocated on that land. But when there is a shortage of water, so the model allocates different crops which are drought resistant crops. So in that is a complex thing. I didn't represent on this one, but that's the extension one. But we didn't prioritize any demands. All demands are set simultaneously dealt. Then the water is allocated for different demands. And if there is unmet demands, there is penalty for that. There is compensation for that, either in terms of monetary. For instance, if the irrigation demand is not met 100%, there is a penalty for that. So the penalty can be compromised. Either you have to buy water from other sectors with that amount of money, or something like that. That is how it trade off the water imbalance between the different water demands.
Okay, thank you very much, Dr. Centeno. Maybe on the optimization, and maybe if you have just, okay, that's very clear, but what kind of optimization did you actually do? Is it a genetic algorithm or none? Can you, I don't know, maybe you can highlight a bit.
Actually, it's a mathematical algorithm. It's a linear programming algorithm. We develop a mathematical setup. Then after that, we transform that or translated the mathematical algorithm into a script. Then actually it is one part of the mathematical algorithm. It's actually generic algorithm that can be applied anywhere, any aspect of the transboundary water system.
Okay, thank you very much.
You're welcome.
All right. I think I can see
Professor-
Anika is in the house.
Yes, she's there. This is what I wanted to tell you.
Okay. So, hello, Anika.
Can you hear me?
Yes, we can hear you.
Wonderful. Sorry, we're setting up internet here. I'm currently at a retreat, so it's we had to find some special ways to get access, but hopefully it works.
Okay, great that you made it. Okay, so Anika, maybe you can, let me introduce you, and then you can do your presentation, and then we can continue with our discussions. So,
sorry, I thought my presentation was at 9 o'clock. Yeah, 9 o'clock.
Sorry, Anika.
So I'm giving my presentation now.
Yes, you are supposed to be presenting now. Do you have your presentation ready?
Yes, I do.
Okay, and before you share your presentation, I want to introduce you to the panel, to the members here.
Sure, great.
Thank you. And so Anika is a PhD researcher, Department of Hydrology and Hydraulic Engineering. Wow, I don't know if I can pronounce this one, Verite, University, Brussels. And she's going to do the presentation on the impacts of climate change on the water, energy, food, and environment nexus in the upper White Nile Basin, a Lake Victoria case study. So Anika, the room is yours. You can share your your slides, and then you can continue the presentation.
Great, thank you very much. Can you see my screen?
Yes, can you put in slideshow? Yeah, great.
You see it as a slideshow?
Yeah, that's okay now.
Fantastic, great. Thank you so much for the introduction. And to help with the pronunciation, we just say Free University of Brussels to address that challenge. So as mentioned, I'm working on the water, energy, food, environment nexus in the Upper White Nile Basin. Now, I think everyone here is quite familiar with the interdependencies and interlinkages between natural resources. And the water, energy, food nexus is a framework that tries to explore how the trade-offs and synergies between these resources can be impacted by how we manage our resources, and also especially under climate change. And so, of course, if we change one of these resources, it impacts the others. So we require water, of course, to grow crops, but we also require it for hydropower production. So any changes in water quantity and also quality will thus impact the access and the creation of these other resources. And my research focuses on the interlinkages between these resources, specifically in the Upper White Nile Basin. And this is the Lake Victoria Basin and the Victoria Nile Basin together. And we can see it here outlined in a pink line. And so it's just a kind of an extended Lake Victoria Basin, so now encompasses approximately 70 million people. And as I'm sure you're all very familiar, it's very important for fisheries, agriculture, hydropower generation, tourism, and also conservation. So there's a lot of fantastic, unique nature there in the area. So to try to understand what some of these challenges are within the area, to try and draw the boundaries within the water, energy, food nexus, so that we can also aim our research to what is the most useful on the ground. Because the water, energy, food nexus, the boundaries don't exist. You can include everything. So to try to make research relevant and useful, we have tried to undertake some stakeholder consultations within the basin to try to understand what needs to be addressed, what can we use science for. And so across the last 2 years, we have undertaken interviews in Uganda, Kenya, and Tanzania with 18 stakeholders related to different parts of the nexus. And part of the discussions have focused around what are the greatest environmental pressures? What are some of the impacts of these pressures on the environment? Where do humans come into this? Well, what policies are trying to address these issues, and where are some of the gaps? And so this has been trying to unpick what are the recurrent themes coming up between stakeholders. Where can we see what the priorities should be? And these stakeholders have included both ministries as well as NGOs and resource managers. And this here is just a quick visual to show some of the things that have been coming up most frequently. And you can see also that there's a big overlap between the different areas of the nexus. The idea of the nexus is to break down a siloed approach, and so exploring the issues can also not be done in a siloed approach. This here is just to break it down even more specifically. What are the things that came up across all the different stakeholders? So here in the bottom, we can see that the 18 different stakeholders were grouped based on the areas of the nexus that they are relevant to. And then on the side here, we see the percentage of stakeholders that discuss these topics. And you can see that water quantity and water quality are some of the most pressing issues that were discussed by either all or almost all stakeholders. Food security in terms of fisheries was also a very important topic that came up a lot, including land degradation, both in general, but also in terms of wetland and forest degradation. And the uncertain impact of climate change on the nexus came through the different topics, both in terms of its impacts on crops, because of the reliance on rain-fed agriculture, but also the impacts of climate change on the lake levels and the river flow. And this, of course, has further spread impacts. So this was very useful in terms of signposting the different pressures and the impacts and what are the highest priorities. But then to understand where some of these are spatially, we applied a conservation tool. It's called Costing Nature. And it allows you to analyze a whole suite of ecosystem services, which are the benefits that humans derive from nature, as well as the pressure on these. So this map here shows the greatest relative pressure from all of these different pressures listed on the left. And each color just shows which of these pressure is the greatest in this area. And we can see that agricultural intensity dominates. So this can tie in to perhaps what are some of the drivers of the impacts that were discussed by the stakeholders. And then also population and deforestation are quite prominent, especially in the northern parts of the basin. And so we've tried to then combine both this spatial analysis of the pressures on the environment, as well as the stakeholder interviews. And we found there's quite an agreement between the things that are being said, whereas one shows the spatial distribution of the pressures, and the other one unpicks more what are these impacts and what does this actually mean on the ground. And this is then has been combined to develop a set of water, energy, food, environment nexus indicators that then allow researchers to explore this topic in a way that is relevant to the Lake Victoria Basin or the Upper White Nile Basin, to try to really make sure we are not allowing pressing topics to fall behind in our research, because again, there are many scientifically interesting things, but whether they are relevant is another matter. And so here you can see a summary of some of them, and it includes things like water quantity, water quality, in particular nutrient pollution, sediment transport, hydropower production, and in terms of food, we can see that there's both crops and also fisheries, and fundamentally also the environment is being included. And things like aquatic biodiversity or biodiversity in general are very frequently left behind in these discussions. But of course, if biodiversity collapses, then there is no more ecological foundation for anything else. So if we have no more biodiversity, we have no more natural resources to manage. So it's very key to also make sure we don't forget this component of the water, energy, food nexus. And so this here is just to try to summarize again, where are the key parts of these indicators. So along the top, we can see the different groupings of the stakeholders as we had before. Along the side, you can see the different indicators. And you can see that every proposed indicator was discussed by the stakeholders. So that was the principle, to try to tailor it to the needs to make sure they're fit for purpose. And also shows then the different priority areas for future research. So what are the highest percentages of the indicators that were discussed by the stakeholders? So again, it particularly addresses water quantity, water quality, food security, and then the environmental factors of aquatic biodiversity and land degradation. So the idea of this being that future research can then be informed by the concerns on the ground. So we undertook some preliminary modeling work to try to explore a subset of these indicators. This is just some very preliminary work. We are currently working on doing more nuanced scenario work and combining this model with another model. But for now, we used soil water assessment tools, so SWAP+, to look at simulations of water quantity, water quality, and crop yield. And this looked first of all at the historical period, create a baseline, and the future up to 2100. And then we would compare the results from these two different periods. And these simulations were done underneath 5 different GCMs. So we had an ensemble of models. So you then we did the average then, which is presented here. And underneath SSP 5, RCP 8.5 conditions. So this is the business as usual and high emissions scenario. So this is sort of the worst case scenario. And this is just more to test, can we use these indicators? What might happen if we're using these different scenarios? And this map here, a lot is going on, but first of all, we can see the outline here of the basin that was shown earlier, with Lake Victoria outlined in grey. The different lines are the inflows, and then we have the one outflow, which is in ginger at 703. It's enabled right next to the line. And then right underneath, we have a table of how these different indicators are changing between the baseline and the climate change scenario. So this is the impact of climate change in percentage shown. And as you follow along the table, this is showing the channels around the edge of the basin. And so this is showing how the spatial distribution of these indicator changes across the basin. So it's not homogeneous, of course not. So this is really emphasizing the importance of using spatial models to explore the water, energy, food nexus under climate change. And here we can also see that there's kind of a hotspot where things are changing the most here in the southeast. And that's where we have some of the biggest increases in nitrogen, phosphorus, sediment, and flow. But these are likely interlinked. As we can see here, the colored maps, the colored pixels on the map show the change in precipitation. And so we can see there's also the largest increases also in the southeast. So it's very possible that an increase in precipitation results in an increase of runoff and erosion in the southeast. Thus, we have this increase in these different variables. And yeah, this is just highlighting these areas. And we've done an average across the entire basin for some of these different indicators to see how we can explore them. And here we can see, yes, an increase in pollution, total nitrogen, total phosphorus pollution, as well as sediment yields, thus indicating a decrease in water quality, but an increase in river flow. But we can also see quite a large decrease in different crops. And here on the right, we have the normalized indicators that we can compare between each of them. And there you can see a large decrease in water quality, an increase in water quantity. This we have very simply just said an increase in water quantity means an increase in energy. So this is again very rudimentary, and a smaller decrease in crop yield. So fundamentally, it is likely that climate change may have impacts on the different resources, which might be driven by increases in precipitation. And as we saw previously, these trends are spatially heterogeneous. So in conclusion, co-creating with stakeholders can strengthen the relevance and application of research. And in this case, we use it to develop indicators and explore the issues on the ground. Climate change will likely have impacts on these different water, energy, and food resources within the Upper White Nile Basin. But it's also important to consider how this changes in different areas. So again, it's spatially heterogeneous, and there's always uncertainty within these analyses. It's also, of course, important to consider these interlinkages and interdependencies between the natural resources so that we can try and minimize the trade-offs. So the next steps is how can we apply this information to try to see where different hotspots are and how to make sure we use these in the most cohesive way possible. And future adaptation strategies must ensure that water quality and aquatic ecosystems are accounted for, both within policy and also any adaptation strategies, and also then scientific research, particularly because within the water, energy, food nexus, water quality and aquatic ecosystems are very frequently left behind. That's it from me. Thank you so much for listening. I appreciate the time.
Thank you very much, Anika, for that great presentation on the impact of climate change on water, energy, food, environment nexus. Yeah, let me check some questions in Q&A and okay, we have question from Mohammed. Ms. Anika, thank you for the presentation and good luck for your PhD. Would you please elaborate a bit what you intend by Victoria Nile Basin, and what is difference from the Lake Victoria Basin? Mohammed, maybe you can ask your question straight away. Mohammed, are you around? Okay, Anika, maybe you can go ahead if you understand the question. All right.
Sure, I think I understand. I think I'm still sharing. I can go back. So in terms of, you mean the area chosen, so the Upper White Nile Basin, this is using the definitions by the Nile Basin Initiative, so we can see The pink line shows that outline, and the Lake Victoria Basin is fundamentally the lower bit and usually stops just on the northern shore of the lake, whereas the Victoria Nile Basin is the basin just downstream of the Lake Victoria Basin. And so thus that includes the outflow, the downstream communities, and also Lake Choga. So I don't know if I understood the question correctly, but yes, this is the combination of these two basins based on the NBI definitions.
Okay, thank you very much, Anika. I think that clarifies. I don't see any other question on the Q&A, but maybe, Anika, I can ask you a quick question. And the first one is on the emission scenarios you used. You kind of use the business as usual on the high emission scenario. SSCP 5 or RCP 8.5, which why you didn't consider the average case where we have some limitation, or why did you take the extreme case?
So in this case, this was more of because it was some exploratory work. And the first thing is to see, would there be a signal in the worst case scenario? So this is just to try to see, can we look at some of these indicators? Would they be changing underneath the worst case scenario? So the next step then would be refining this and having further RCP scenarios, also in combination with further SSP scenarios that have been made regional, because absolutely it's only so useful to have the baseline and one very bad future climate change scenario. So this is again just preliminary exploratory work, and the next stage is to refine this to hopefully make the findings more relevant to what might actually be happening.
Okay, thank you very much. Yeah, let me ask another question again to the I think I'll ask Engineer Abdallah Mohammed. I think my question was also on the validation or calibration of the remotely sensed WRPO data, but I think you already explained that one on how it's already calibrated data. But there is also another question on what were the findings regarding water productivity and irrigation performance in the Managil zone and the southern Gezira zone? How do these findings compare to the optimum levels?
The optimum levels for what? Sorry, I didn't quite hear.
I think that was more asking actually Engineer Abdallah.
Oh, sorry.
Yeah.
Wait, so this question is for me?
Hello, Anika. Yes. I'm done with you. I was asking.
Oh, sorry.
Yeah. Now it's Q&A for the whole group now. Thank you very much. Sorry.
I understand. Sorry. I'll stop sharing my
You
screen.
can just remove your sharing and it goes okay. No?
Yeah.
You can just remove your slide. Okay, thank you. All right, good. So members, I'll be just asking questions randomly to specific people. And then after that one, then we'll go to the general panel discussion. We have some guided questions which we are going to brainstorm. But before we go to that, let me just ask, I don't know if Engineer Abdallah is still around. Maybe he's kind of disconnected.
Yes, Prof. John.
Okay, good. So,
yes.
Engineer Abdallah, I'm not sure if you got a question.
Could you repeat the question, please?
All right. The question is on the performance. I mean, what were the findings regarding water productivity and irrigation performance in the Managil zone and the South Gezira zone, and how do this compare to the optimum levels?
Yes. For Managil zone, the productivity is around 4 to 6 ton per hectare. When you compare it with the south part of the scheme, the South Gezira, it is 2 ton per hectare. So the Managil zone, they have high production and also high water productivity. They use optimum water use. And the farmers there, it is they apply the best practices developed by the Agricultural Research Institute, and they follow the best practices rules.
Okay. Okay, thank you very much.
Yeah, they almost produce double the South Jazeera Managil zone in terms of productivity and also in terms of water productivity.
Okay, thank you very much. Soliman, on the modeling of the wetlands, I have some few questions as well. And one is on the delineation of the wetlands and I mean the boundaries of the wetlands and how did the modeling? I know that you use a grid-based model to model the catchment, what kind of water balance.
Exactly, yeah.
Yeah, so I was asking, did for the rainfall, for all the data you considered remotely sensed data, or you had some ground-based measurements for example, rainfall?
Okay, we used the remote sensing data or rainfall estimate data. We used the SHARES, but before that we were working in another project with Nile Basin related to the climate service infrastructure, and we tried to find which satellite rainfall estimate data are adequate for the Nile Basin by comparing it with the observational data along the Nile Basin. And we found that SHARES has the highest performance evaluation to resemble the observation data sets in the whole Nile Basin, yeah. Starting from the Ethiopian Plateau to the Uganda and the Kagera Basin in Rwanda and Burundi. So what we found that the SHARES resembles or matches very well the observation meteorological gauges. That's why we used SHARES to as a precipitation data input for the wetlands.
And then for evaporation, because it's one of the very important components for the water balance in the wetlands?
The same thing we have done for precipitation, we have done it also for evapotranspiration, but firstly we calculated we acquired the temperature data, okay, from the World CLIM reanalysis data sets, if you know the World CLIM reanalysis data set. And also we compared it with the observational data sets, temperature data sets in the Nile Basin, and we found also World CLIM yields very positive performance evaluation in terms of maximum and minimum temperature. And using the temperature, we used the Blaney cradle method to estimate the evapotranspiration. Why we used Blaney cradle? Because this is for two reasons. First reason is it's a simple method, requires just temperature. Second reason, it's suitable for tropical areas and also it's areas which are not characterized by high change in temperature along the marshes. But also we could use another empirical methods to estimate the evapotranspiration, not just the Blaney cradle. We could use, for example, Hargreaves, but we need actually a simple method because we don't have a lot of data related to the relative humidity and the wind speed, for example, because there are more complicated data sets that requires this kind of data, such as Penman-Monteith, for example. Yeah.
Okay, thank you very much.
Yeah.
And then maybe the final one is on the dynamic inundation maps in the wetlands you have produced from this particular study.
Yeah.
Just wanted to find out what could be the application of these maps, and especially when you look at future management of the wetlands in the Nile Basin.
It's very good question. Actually, there were a developed methodology to correlate between the status of the wetlands in terms of inundation depths and soil moisture. And this was conducted before that there were an ecological rule matrix conducted for the Nile Basin between the wetland hydrological characteristics, and the ecosystem services, or the land, not really the ecosystem services, but the vegetation unit dominance. Like, for example, if the inundation depth is above 2 meters along the year, then this area is considered as a permanent wetland. And if we classify the land cover according to the wetland status, we could identify the ecosystem services. Maybe I can share something, or
yes, please.
Because there were like an evaluation matrix which is explaining all that stuff. Can I share my screen?
Yes, please go ahead.
Okay, so here is the evaluation matrix. Okay, this was conducted before by a previous study for the Nile Basin. Okay, and in this evaluation matrix, there are 6 types of classification for the wetland: open water, aquatic vegetation, fringe, papyrus, reeds, grass, and trees. Okay, and based on the soil moisture index and the water inundation depths, okay, and also based on the percentage of duration or inundation duration for this vegetation unit along the year, you could identify what is the dominant status of the wetland, if it's open water, if it's aquatic vegetation, and so on. And based on this classification, we could identify, or we could actually identify the different ecosystems. Like, for example, in open water, there were also a study conducted by previously, that there were a relation between the vegetation unit type and the ecosystem services. For example, open water is adequate for fishes, papyrus and reed is adequate for raw materials and fuel. The grassland and shrubs are adequate for livestock and etc. So based on this evaluation matrix, we could quantify the ecosystem services in the future. If we build or develop different development scenarios, okay, by changing the land use or changing the activities, we could use this evaluation matrix as well to project the future status of the wetland. Maybe this elaboration could let you better understand how could we relate it.
Okay, thank you very much, Soliman. I think that is very important elaboration. And yeah, in the Q&A, we have one question to Anika. It says, Anika, there's one question to you. It says, how do you see about management issues regarding to optimal utilization of water resources in the project area?
Thank you for the question. So in terms of future use of water, if this is what the question is about. We will be working with some collaborators at IASA to try to understand water demand, because our models can only show about water quantity. And so there requires some pre-processing to also understand if the available water meets the water demand so that we can optimize the water use. But it's not an optimization model in itself. So it's not like we can say to the model, we require this amount of water for agriculture, this amount of water for hydropower, and then it finds the optimal scenarios by running hundreds and hundreds of different possibilities. But we can say how much there is, and then explore underneath different scenarios whether this is sufficient for then agriculture and hydropower and domestic use. But that requires pre-processing after we have run our scenarios. But there is some fantastic optimization work out there. That's just not what our model does in this case. Thank you.
Okay, thank you very much, Anika. Yeah, and then there's another question from Mohammed. I think is going to Engineer Sami. I think it's probably is this meant for. It says, do you think that machine learning and artificial intelligence and remote sensing and Earth observation, global hydroinformatics, and big data and climate change adaptation, among other almagnable approaches used in modeling and flow forecasting will change the narrative in the Nile Basin management? I think maybe it goes to Dr. Osman. Mohammed, maybe if you can ask your question straight away and you can.
I think Engineer Sami, I think he's around. Maybe.
All right. Okay.
If you give him the chance, maybe.
Engineer Sami, are you around?
Sami?
I'm around, honestly, but right now I'm on a plane. So I can answer if can you just repeat the question, please?
Okay, the question says, do you think that machine learning and artificial intelligence and remote sensing and Earth observation and global hydroinformatics and big data and climate change adaptation, among other almagnable approaches using modeling and flow forecasting, will change the narrative in the Nile Basin management?
Yes. First of all, thank you for that question. Yes, that's basically what we do here in NBI, especially in NELSAP and generally in NBI. We use all these. We use machine learning, we use decision support systems, the Nile Basin decision support systems, and other models using remote sensing, using the measured data from hydromet stations. And yes, in NBI, what we do is we enhance the collaboration between the two countries, and we show these scenarios of collaboration versus non-collaborations. And most of the results shows that when you depend on your own without communicating with other downstream and upstream countries, you will suffer. So, and these new technologies like machine learnings and remote sensing and all the others, and AI, of course, helps to, first of all, do multiple scenarios and run different scenarios and show different results. And from there, you can do the Pareto set for optimization, showing which scenarios are best fitting, and also multi-criteria analysis, of course, which scenarios are best fitting for application of these collaborations in terms of operation of the whole system of the Nile Basin. Thank you.
Thank you very much, Engineer Sami. Yeah, for the interest of time, let me now go to the general questions and general guiding questions for the panel discussion. And this is not very specific to any individual, but I think we can discuss. So we have two questions, which are two guiding questions for the panel members. And one is, because our topic, remember, is hydrological modeling and flow forecasting. So what are the recent advances in hydrological modeling and flow forecasting? And the second one is, how then can the Nile Basin take advantage of these new developments in establishing equitable utilization of water resources? So maybe I throw this one to the group, and I don't know who Engineer Dr. Osman. I don't know if you can start the first one, or anybody else who thinks can start with
Yeah,
that.
I think, Engineer Sami, I think, dwelled on that, the work they're doing. Advancement in technology now is helping a lot, especially when it is linked with ground truth. And I think this is helping us, and the Nile Secretariat is doing a lot of work on that one, the resilience support system and the other activities. Dr. Zarrouk is around. Maybe he can respond and show how the Nile Secretariat is using those new technologies, adding to what Engineer Sam has said. Thank you.
Thank you very much, Dr. Osman.
Okay, Professor, can I react on that?
Yes, please, Dr. Cynthia.
Yeah, actually, I mean, the advancement in hydrological modeling and river forecasting has contributed a lot. Nowadays, the use of integrated remote sensing and GIS technology have improved the modeling of hydrological assessment, especially utilizing high resolution remote sensing and GIS data for better understanding land use change, and also for improving of the key hydrological parameters in order to get a very precise output. And also the introducing of machine learning and AI also has a contribution in handling of large data sets, and also it improves accuracy in prediction of the hydrological models. And also nowadays we start to use ensemble forecasting, integration of multiple forecasts to account for uncertainty and enhance forecast accuracy, and also using of data assimilation into model in real time to improve model, and also using of hybrid models, combining of traditional physical based models and the data driven approach for better accuracy and robustness has also contributed in the advancement of the hydrological models and improving the parameters. Also, there is also a real-time monitoring system and also improved model calibration. And also nowadays there is citizen science, integrating with citizen science, involving public in data collection, validation with citizen science, that initiative to enrich the data sets and also to improve the hydrological modeling. These are some of the advancement that is contributing in the hydrological modeling and the river flood forecasting. That's what I want to react on it.
Thank you very much, Dr. Cynthia. Anika, I know you're also using the SWOT plus for water quantity, water quality, and crop yield modeling. What's your reflection on that question?
Well, one of the great things, and also with this forecasting, is how you can, it's a very long process of calibration, but this then means that we can also, it can quite accurately represent the different flows of a region. So one of the weaknesses is we require data for calibration, but then one of the strengths being that then for forecasting, because you've had such an intensive calibration process using flow data, then when we are doing forecasts into the future, there's quite a lot of validity behind results. And of course, there's a very big variety in hydrological models and how they address this. This varies a little bit more for water quality. That's something that's ongoing, but for water quantity, SWOT plus has worked very, very well also in data scarce regions. So that's one of the issues that we are facing with other parameters in the Upper White Nile Basin, is that data scarcity can make calibration validation more difficult. But at least for flow, we have good data, and so we can, it adds validity to our results for forecasting into the future.
Thank you very much, Anika. Any other reflection on that? Okay, maybe in connection to that one is then, how can the Nile Basin take advantage of this new development in establishing equitable utilization of water resources? We talked about optimal transboundary water allocation. We talked about water, energy, food, and environment ecosystem nexus. So, Anika, do you want to comment on that one?
Yeah, sure, especially the latter. So, I mean, it's already explored in quite detail at the NBI in terms of the connection between resources. But I think this is something that really needs to be capitalized upon in future research and also policy work, because as we all know, these deep interconnections between the resources exist. So when we are undertaking our hydrological models, not to forget the system that this sits in. So again, the impacts how water extraction and changes in water quality, the knock-on effects this has on other sectors. So I think capitalizing upon the water, energy, food, environment nexus, thinking about model coupling, it can be simple model coupling. We're doing soft model coupling between an ecological and hydrological model. But then also thinking about the inputs into these models and to not lose that connection with agriculture, with the environment, with energy. And especially when we're then thinking about forecasting into the future, there will be there already are many big pressures on all these resources, but these will be changing even more. And so I think within the NBI, making sure we are using some of the best up-to-date data, as we've already discussed, remote sensing data, how powerful this can be, and especially for the water, energy, food nexus, there's a lot of fantastic available tools of how we can incorporate this. But not to lose sight of these interlinkages, especially across the whole NBI, where there's a lot of changes happening. Thank you.
Thank you, Anika. Maybe I go to Engineer Abdallah. You presented about the water productivity tool. I mean the WAPO data from FAO. How do you think can that be utilized? I mean, in terms of and inform, and it can be used for establishing the equitable utilization of water resources in the Nile Basin.
Of course. Yes. Actually, the WAPO portal is an advanced tool. And it is the first tool in the world that containing the data of land, water, and climate on one portal. And the data time step, it is every 10 days, we have a new layer, every decadal data. And also, as I mentioned, from the 4th of October, we cover the whole globe. And actually, this WAPO portal is already used by the NBI for the water accounting project, and this tool can be used for equitable use of water in Nile Basin countries. Thank you.
Okay, thank you very much. Any other contribution from the members? Yes, Engineer Sami.
Thank you very much, Doctor. Yes, just to give also some insight of several projects and several models that right now NBI is using. If anybody can just go to ikp.nilebasin.org, you'll find that we have flow forecasting, we have flood early warning system, flood forecasting, we have drought forecasting. We are currently developing a flash flood early warning system. So these and of course the Nile Basin decision support system itself, with others. So there are several models and several results and several studies that were done in terms of how to cooperate and how to also do an equitable utilization of the water resources of the Nile Basin. And this is basically the shared vision objective of the NBI itself. And I believe also NBI, when it becomes a commission, which is after the approval of the CFA, the Cooperative Framework Agreement, this will also become a step forward for the equitable utilization of the water resources of the Nile Basin. Thank you.
Thank you very much, Engineer Sami. Any other contribution? Okay. So if no any other contribution, I'll thank you very much, panelists, for the great presentation and discussion we had today. And I think it has been very informative in terms of the future of hydrological modeling and flow forecasting, and then the issue of equitable water allocation and the transboundary water, considering also the water, energy, food, and environment nexus. So thank you very much. Before coming to the end of our session. I'll take this back to the Secretariat if they have any further announcements. Thank you very much. Back to you,
Thank
Secretariat.
you. Thank you very much, Prof. Joel. We appreciate very much your outstanding moderation for this important session. And we would like to thank also all the panelists and speakers for their informative and good presentations. Allow me also to thank you for the good panel discussion. And also behind the scene here, allow me to thank Vincent, our young professionals, Dr. Azza, Suwaid, and Patrick, and Marushka. They did also a lot of work behind the scene to make this session successful. The last thing I would like please to invite all the participants also for tomorrow's session. We have tomorrow at 9 a.m. also an important session about strategic water resources analysis, a planning tool for meeting multisectoral water demands in transboundary river basins. Please also join us in tomorrow's session at 9 a.m. Thank you all and bye-bye. Thank you.
Thank you. Thank you.
Thank
Thank
you.
you so much.
Thank you.
Thank you very much. See you.
Thank you.
Thank you so much.